Let's sum up at this point where we were and what the state of affairs was about the year 1900. The state of affairs in about 1900 was very simply that we had two types of things that existed in the universe. We had particles that had mass and charge located at certain position vectors Ri with velocity vectors Vi and momenta Pi that obeyed Newton's second laws of motion, which basically said that the time derivative of the momentum would be equal to the total force on the system. This had been developed over the last over 100 years and explained all of the particles that had mass. But then there was another thing that had come into existence, and that is the concept of the electromagnetic field. And in fact, we had learned from Maxwell's work in the 1860s that the electric field, the magnetic field, and light itself were not three separate disciplines, but all manifestations of one object, the electromagnetic field. And so the linkage between particles and the forces exerted on them, particles that had charge and the forces exerted on them, was given by the Lorentz force equation. Force, in this equation here, is the charge times the electric field at that point where the particle is located, plus charge times the velocity of that particle, crossed with, where this is a cross product, the magnetic field. Now this force is to be placed in here, and for each one of the particles, of which there may be 1 or maybe 1,000, the time derivative of the momenta of the ith particle is given by this force, where this Q is the charge on the ith particle, and the electric and the magnetic fields are the forces, are the fields where that particle is currently located. And of course, as the particle moves, then of course those fields effectively change in what force they give. Then finally, we have the electromagnetic fields themselves. They are determined not only by each other. In other words, as we know, the derivative of the electric field gives us a new magnetic field, and a changing magnetic field gives us an electric field, but also by the currents J, the current densities and the charge densities due to the particles. So this becomes a coupled system of Maxwell's equations and Newton's equations linked by this force equation, which says the particles exert a force and alter the trajectories of the particles, the electric and magnetic fields do. And conversely, as these particles move around, they have positions and they have velocities, which give rise to charge densities and currents, which give rise to new electric and magnetic fields. This is further complicated by the fact that the changing magnetic fields also give rise to these fields. Thus, Maxwell's equations for matter, linked by the Lorentz force equation to electric and magnetic fields determined by Maxwell's equations, give a closed deterministic system. This is augmented by the Newtonian gravitational force and the gravitational field, which will be treated separately. Given that scenario, everything would seem to be really easy and straightforward at this point. Thus, it would seem that we really had nothing to worry about. We have coupled systems of equations. They're difficult to work. However, something new emerges from Maxwell's equations. That is, we can seek solutions to Maxwell's equations in the vacuum, non-trivial vacuum solutions. When there are no charges and no currents and no particles at all, is it possible for electric and magnetic fields to exist all on their own? And we're going to try solutions to Maxwell's equations of this form right here, where we have an electric field only in the y direction, and the x and the z direction vanish. And it's an oscillating field with a wave number k, which is just a constant times x, minus omega times t. This will be a wave traveling in the positive x direction. And a magnetic field in the z direction only, and therefore bx and by are to vanish, which is a constant times a cosine of kx minus omega t. We notice that these two wave numbers are identical, and the two frequencies, omega, are also identical. The cosine forms are identical, and this is a requirement in order for these to be a solution. So we're now going to plug these into all four of Maxwell's equations and make sure that this works. We first put this into the form del dot E, and here we have the partial of Ex with respect to x, Ey with respect to y, and Ez with respect to z. Must equal to 0 because there is no charge density on the right hand side. Well, that works because if we look at this, that this term automatically vanishes, this term vanishes, and the derivative of the electric field in the y direction with respect to y vanishes because there's no y component here. And therefore that partial derivative vanishes, so this equation works. By that same token, del dot B also works because Bz contains only the component x, so partial of Bz with respect to z vanishes. Likewise, both of the Bx and the By vanish, so they vanish also. So the first two of Maxwell's equations trivially work. We now go to the next equation. This requires that del cross E is equal to minus d by dt of the magnetic field. And when we go through this term, we see that, we recall that Ex and Ez automatically vanish. So this vanishes, this vanishes, this vanishes, and this vanishes. Likewise, the partial of Ey with respect to z vanishes, so this vanishes, leaving only a single term where I put the star. On the right-hand side, we have the time derivative, and of course Bx and By vanish, and only Bz will be non-vanishing. We put that term over here on the right-hand side. Let's write out what those two starred terms are. This term here must equal, as a third component, this term here. Automatically, we can see that the first component 0 is equal to the first component 0. The second component is equal to the second component. So we're really here only looking at the equation where this third component, this starred component, is equal to this starred component over here. There, we now take the derivative of Ey with respect to x. The derivative of Ey with respect to x will give us a minus k out here, because we're taking the derivative of the cosine, which will give us negative of the sine, times Ey times the sine of kx minus omega t. Taking the negative of the time derivative of Bz, then we have the negative of the time derivative of cosine gives us the negative of a sine. The derivative of the time gives us minus omega out front. We have a B0 sine kx minus omega t. Obviously, the sine of kx minus omega t cancels from both sides, and that's why from the start it was absolutely critical that, the cosine terms for both the electric and the magnetic field both depend upon the arguments in exactly the same way. From this equation, we then see that E0 over B0, here we have a minus sign, here we have three minus signs, so the minus sign vanishes, the sign is gone, and we can write E0 divided by the B0 over here is equal to the omega over here divided by the k that's over here. In this equation right here, E0 over B0 is going to be equal to, now we have to pause for a moment and look at what the ratio of omega and k are. Now if we're following a wave with a constant phase, then kx minus omega t on that wave is going to be a constant. So we can take the differential of that expression and we get k times dx minus omega dt is equal to 0. Bringing this term to the right-hand side, dividing through by dt, we get dx dt is equal to omega over k, which must be dx dt, the velocity of light. Consequently, we find that omega over k is equal to c, an important formula here that we want to put a square around and remember. Likewise, E0 over B0 must have the ratio of the velocity of light. So we have our first restriction. In order for these two expressions to be solutions of Maxwell's equations, We've automatically satisfied the first and the second, but the third imposes a restriction on the ratio of E naught to B naught that they must be equal to C. It also tells us by this small derivation over here that omega over k is equal to the velocity c. We now take the fourth of Maxwell's equations, and the fourth of Maxwell's equations, we get the following. Del cross B, which is given by this expression here, must equal to, recall now that the current is vanishing, mu naught epsilon naught d by dt of the vector field E. Here we see that, we recall that, first of all, that bx and by vanish. So here's by, bx, by, and bx. Finally, bz, derivative with respect to y, vanishes because bz does not contain y, and we're only left with the partial bz with respect to x, which is this term here. Every other term, this term here, sorry, every other term vanishes. Likewise, over here, ex and ez automatically vanish, and we're only left with ey. Now equating, we see that that means that the first component is 0 and this component 0. The third, or z component 0, third component 0 over here. So that part of the vector equation is satisfied. We now only need equate this one term here to the derivative of ey. When we do that, we take this derivative of bx with respect to z. I'm sorry, bz with respect to x. bz with respect to x brings this term down here. We automatically have a negative sign because of the derivative of the cosine, which gives us minus a sign. The derivative of x brings out a I have a minus k here. We have the minus k comes from the fact that we have a minus sign here. So we actually have two signs, one that comes from the derivative of the cosine changing it into a sine. The other one comes from the fact that we have a negative sign here in front of our term. It gives us two minus signs which will cancel. A b naught times k times the sine, kx minus omega t. On the right-hand side, we must take mu naught times epsilon naught times the electric field in the y direction, derivative with respect to time. So that gives us mu naught epsilon naught, and the change with respect to time will give us a minus omega out front, but also another sign because of the cosine being changed into the sine. So we get two negative signs that also cancel, and that leaves us with this equation right here. Now all of the negative signs cancel out with one another. As I mentioned before, the sine cancels with the sine, and we're left over here with k times b naught must be equal to mu naught epsilon naught e naught times omega. Or, if we look at e naught over b naught, here's the e naught over b naught, omega over k, in other words, we divide through by this, and we also divide through the other side to get a 1 over epsilon naught mu naught. We get e naught over b naught, omega over k, is equal to 1 over epsilon naught mu naught, but e over b naught is equal to c, and omega over k is equal to c, so this term here is equal to c squared. So now we get the restriction that c squared must equal to this, or equivalently, the incredible result that the speed of the electromagnetic wave as it travels along has to be exactly 1 over the square root of mu naught epsilon naught. This, believe it or not, is one of the most earth-shaking conclusions that we could get, because it tells us that Maxwell's equations imply that the electromagnetic wave can not only be predicted from Maxwell's equations, which is all forms of light and electromagnetic radiation, but that the velocity of that wave has to be a particular velocity. Now, this is totally in contrast in contradiction with Newton's theory. And we will learn about that in just a second. First, let us bring together all of the conclusions that we have made from the derivation on the last page. First of all, we found that E naught over B naught must be equal to the constant C. And what this does is allows us to have any value whatsoever for E or B, but this ratio determines what the other constant is. So, for example, we could let B naught be any value. Then E naught is C times B naught, and it's determined. That means the wave as a whole can have any amplitude, but we may not have an independent amplitude for both the electric and the magnetic field. The ratio of the two must always be the speed of light. That's result number one. Result number two is the ratio of omega to k must be the velocity. And k is the wave number, omega is the angular frequency. And each of these, the frequency can have, or let's say k can have any number that we choose. But once we choose k, omega is fixed by this equation. And they must be in the ratio of the speed of light, or c. Finally, or next, we find the incredible result that the speed of light itself is 1 over the square root of the product of these two constants that come from Maxwell's equations. Thus, the speed of light in a vacuum is constant and is determined to be a fixed value. That result in itself is at the foundation of special relativity. It tells us that no matter what type of transformation group or Lie algebra that we invoke on the system, the transformations must be such that to any two observers the speed of light must be the same. It also is in direct contradiction to Newton's equations. There was a phase that could have been put into the last equation in the form cosine of kx minus omega t plus delta. And if you look back through those equations, you'll realize that we can set that phase to any value that we choose. That, of course, means that we can just orient the coordinate system relative to where the wave has its maxima and minima any way we choose. However, that phase must be the same in order to get the cancellation between the electric and the magnetic field. They must be in phase with each other in their oscillation. So, summarizing for number 4, we can have any relative phase for the wave as a whole, but that phase must be the same for both the electric and the magnetic field. They are in phase with each other. Next, we notice that kind of automatically out of this solution that the electric field, the magnetic field, and the direction of the wave are all perpendicular to one another. Why was that? That was because we chose an EY and a BZ, and we found that the wave propagated in the x direction. Therefore, we have this picture of the electric field oscillating in the y direction, the B field oscillating in the z direction, and the wave traveling in the x direction. One could set out to say, I choose solutions that do not have that property, and we would find that they would not be solutions to Maxwell's equations except when these two are perpendicular. And when they're perpendicular, they always give a wave solution that travels in a perpendicular direction to that. Finally, the wave can of course travel equally in any direction. Summarizing the entire thing, we can see that we can have any value to the wave for the amplitude of the wave, but the electric part is fixed with respect to the magnetic part. That we can have any wave number or any frequency, but the wave number frequency ratio is fixed by the speed of light. There is only one possible velocity at which the wave can travel, 1 over the square root of epsilon naught mu naught. The waves can have any phase. However, the electric and the magnetic field must be in phase with one another. And the electric and magnetic fields are both perpendicular to each other and to the direction of motion. Finally, the wave could travel in any possible direction. It does not have to be in the x direction, and therefore you can have mixtures of the electric and the magnetic field that would be obtained by taking these solutions and rotating them through any element of the rotation group. This brings us now to the theory of relativity. We have learned in the past that Newtonian space and time are separately conserved. In particular, we know that length is invariant. If I measure in my reference frame the length of a meter stick to be 1 meter, then everyone else in all other moving frames and still frames, however oriented, however translated, and however moving, will all see the same length. Now we note that that is actually motion under 3 different group transformations: rotations, translations, and the transformation to a moving frame. And length is invariant under all of those according to Newton. Likewise, time is invariant to all of those observers. That means time flows at a constant rate no matter what your relative position, your orientation, or your relative velocity. So Newtonian mechanics has 2 invariants: length, and according to the Pythagoras theorem, that would be the square root of x squared plus y squared plus z squared, where x, y, and z are the relative distances between 2 points, and the time t. I emphasize again, length is an invariant and time is an invariant. We will find out in relativity that there is an invariant, but length and time are combined to give one invariant and are not separate invariants. Let's see how the contradiction of a constant speed of light emerges in the theory of relativity from the Newtonian theory. First of all, we want to look at how velocities add. We can take 2 frames of reference: the S frame, which is this one with the solid line, and the S prime frame, which is the dotted line here. We can see here that if we look at a certain position, right here at this point, its position is a distance x according to the S observer. And according to this observer, if we go from the origin over, it's a distance x prime. If these 2 frames were coincident at time t is equal to 0, then this frame has moved along a distance capital velocity times time in that period of time since time t is equal to 0. We can see that if we put a t is equal to 0 here, they'd be coincident at that time. Consequently, we can see that x is equal to x prime plus velocity times time. Now, taking the derivatives with respect to time, velocity to this observer is equal to velocity with respect to the prime observer plus the relative velocity that's moving. Thus, velocity in the prime frame is velocity in the unprimed frame minus v. So it is impossible for something to have the same velocity relative to both observers. Maxwell's equations give us a constant velocity and therefore contradict this. It turns out, in the long run, that Maxwell's equations are relativistically correct from the start. This is really because the electric and magnetic fields consist of photons, which have no mass and travel at the speed c. Of course, Maxwell did not know that at the time. But it follows that Maxwell's equations inherently had to be relativistic because they're composed of things that could not, namely photons, move slower than the speed of light. In relativity, length and time, as I mentioned, will no longer be separately invariant, but rather a new invariant will emerge, which we will discuss in the next lecture.